As we indicated earlier, a quantum computer is not necessarily an easy thing to make. Indeed, it appears that it's a very hard thing to make. As a result, we can't quite say exactly what a quantum computer would actually look like. But as we said, it would almost certainly work in a very different way from our current digital computers. Here's one basic idea of how it could work. We would have some collection of quantum elements, possibly electrons with spins or atoms. To start the computer on some problem, we would have to prepare those spins or atoms in specific starting quantum states. That would be part of the programming of the machine. We would also design the machine to give particular kinds of interactions between these quantum elements. When we turn the computer on, whatever that means in practice, we would be letting the quantum mechanical state of the whole machine evolve in time, using the designed interactions between the different quantum systems. Possibly, running the machine could involve shining pulses of light into specific quantum elements at specific times. We could think of this loosely as being analogous to a kind of clocking of the system, possibly triggering various required quantum operations. Then, finally, we would read out the state of some part of the system. That readout is a quantum mechanical measurement. Necessarily then, because of the state collapse in the quantum measurement process, we would throw away some of the information about the final quantum state of the system. That loss of information is one of the issues in using quantum computers. Hopefully, however, what we do read out from the final quantum mechanical state of these quantum elements of the system does give us some useful information for the problem we wanted to solve. There could be many different ways in which a quantum computer could work in practice. One view is that we could be using kinds of quantum computing gates that are loosely analogous to the gates we use in conventional digital machines, though we should emphasize that analogy is very loose. So let's see what kinds of gates a quantum computer might use. A qubit itself can be written, as we've seen, as a two-element vector, such as we could use to represent a spin state, for example. So here, a vector like this, two components to it. The necessary basic operations for a quantum computer can be written as 4 different operations. 3 of these are operations on a single qubit. We can write these operations as 2x2 matrices, representing the corresponding unitary operators. One possible set of single qubit operations is this set here. These 3 unitary operators are known respectively as a Hadamard operator, so that's this one, a Z operator, so that's this one, and a not X operator, so that's this one here. Using the Bloch sphere that we've seen before for looking at spin states, we can represent a qubit as a vector, such as the spin polarization vector we looked at before, pointing from the center of a sphere to its surface. Single qubit operations correspond to rotations of the vector on the sphere. Single qubit operations can be achieved in practice for spins, for example, by appropriate pulses of magnetic fields, for two-level atomic systems by appropriate pulses of electromagnetic fields, and for photons by simply changing the polarization state of the photons. 2-qubit gates, the 4th required operation, involve the interaction of 2 qubits in what we call a controlled NOT or C-NOT gate. 1 qubit in this C-NOT configuration is called the control. The other is called the target. If the control is in the state 0, then what is supposed to happen here is that the target qubit should be passed through unchanged. If, on the other hand, if the control is 1, the target qubit is to be inverted. A target qubit of state 0 is to be changed to one of state 1, and a target qubit of state 1 is to be changed to one of state 0. Hence the name controlled not. So only if the control is what we could call high is the target flipped. If the control is low, the target is not flipped. Hence, controlled not. A 2-qubit state is a vector in a 4-dimensional Hilbert space. That is, like a state of 2 photons in different paths. So, as we've written before, something like this kind of a state, which we could rewrite in the notation that we see here. So we're not necessarily talking about horizontal and vertical polarizations, but we could be. This is just a generalization of this kind of state here. So we have, just as we had here, 4 C coefficients, so we have them here. We've just labeled them a little differently. And we can also choose to write those as a column vector. So this is a column vector with 4 coefficients in it because we need 4 coefficients to specify the state of the 2 qubits. The corresponding operator in this 4-dimensional Hilbert space for this C0 gate can be written in the following form. So we want the C0 to express this operator. And we're going to show why this operator would work. For example, the input state with the control as logic 0, that is low, and the target as a logic 1, when written in our form here, would correspond to the following set of coefficients. So this coefficient would be 1, because that corresponds to control being logic 0 and target being logic 1. And all the other coefficients would be 0 in that case. So we could write this state as a column vector, and this would be what it looks like. Well, starting with this state and operating with our proposed unitary operator that we wrote down before, gives the following piece of matrix algebra. So here's our state with control low and target high. So that happened to be a 1 in this element. Here's our matrix, and the result is that the target remains unchanged. It started out control 0, target 1. It ends up as control 0, target 1. That's just the state we started with. As intended, the target qubit passes through unchanged if the control qubit is logic 0. So that's what this corresponded to as a starting state of the system. Control qubit logic 0 and target qubit logic 1. That was the coefficient 1 we had in here. Alternatively, we could choose an input state where the control qubit is logic 1 and the target is logic 1. That would be this state. Control qubit logic 1, target qubit logic 1. And so this coefficient would be 1 and all the others would be 0. Then our input state could be written in the following form. C11 is to be 1 and all the other 3 are to be 0. Acting on this input state with our matrix gives the following matrix algebra. So we come in with this vector, we multiply by this matrix, but note now that this is the non-zero operation, the multiplication of these two, and that means we get a 1 in here. This output state is therefore the one with the 1 in this part in the column. That means C10 was 1. Now the target qubit is a logic 0. It has been flipped. And the control qubit remains at logic 1. And we could check this out also for the other two possibilities of starting states for the target qubit. To implement such a gate, the two systems representing the 2 qubits must interact. If the system representing the control qubit is in its 1 state, we want it to affect the system representing the target qubit. To understand this, we can look at a hypothetical and simplified system. So let's look at our hypothetical 2-qubit gate. We could imagine two different two-level systems, a control system and a target system. We imagine that we shine a clocking light pulse at the target system. If the control qubit is in its 0 state, then this clock pulse, we presume, does nothing to the target qubit system. So it leaves it either in its lower state, like this, so here's our photon coming past and doing nothing, or in its upper state, like this, so here's our photon coming past and doing nothing. If the control qubit is in its 1 state, perhaps it somehow changes a transition frequency in the target qubit system. These two might be atoms that are interacting in some way, for example, and when this atom is in its upper state, it influences the upper state of the other atom through some interaction between these two systems. With this presumed change in transition energy, we now presume we've designed this system so that the target qubit system could then be sensitive to the clock pulse. Perhaps it's now closer to being in resonance with this clock pulse. And so this clock pulse will then flip the target qubit state, implementing the C0 function. So our photon comes along, and now it flips from the low state to the high state. And if we started out in the high state, it flips from the high state to the low state. This above example was hypothetical and somewhat simplified. Example systems for real 2-qubit gates include ions in ion traps, superconducting flux and charge qubits, quantum dots, and spins in semiconductor impurities. A major challenge for quantum computing is that it's difficult to isolate the quantum mechanical systems enough from their environment. Consequently, the phase of the quantum mechanical system keeps being disturbed, which destroys the fidelity of the quantum mechanical states being used. Quantum computing relies on the phase of the quantum mechanical states being undisturbed for sufficiently long times. Essentially, we need systems with long dephasing or decoherence times. One possible solution is to use some kind of quantum error correction to restore the state, though that itself requires quantum computing gates. And to run that quantum error correction process, we would still need to be able to get above some threshold number of quantum operations without dephasing. Avoiding dephasing remains a substantial practical challenge in many approaches to quantum computing.